Welcome to the online MOOC course on software engineering. In this lecture, we will look on to data flow diagrams, flow chart and decision tables. So, the agenda for today will start with data flow diagrams followed by structured chart, decision tables and the traceability from high level design to low level design. So, first we will look into data flow diagrams. So, data flow diagram is one of the preliminary technique with which we can convert the requirement to a design phase. Okay. So, here we will try to use the modeling, basically the diagrammatic picture with which we will try to model everything. So, in data flow diagram, the first level of diagram is called as the context flow diagram, which is called as the level 0 diagram. So, the level 0 diagram is called as the context level. So, here we will be using one single process and how it is going to interact from the input to output. So, that is what we call it as a context diagram or a level 0 DFD. So, here you will be having a single process and what all inputs you expect to the system and what are going to be the responses from the system. So, you will have the input, the process as a entity and outputs is going to be the interactions or any output that the system is expected to give. So, now this process is very abstract, you will just name it as a entity, but you will not be exploring much. So, this level of diagram is called as your context diagram or level 0 DFD. So, this process is going to be expanded and will go for the level 1 DFD, level 2 and it goes on. So, the number of levels that we have to go forward is based on the extents you know about the system. Normally, level 2 is much preferred where you will be trying to get the information about the system in a greater extent. So, now we will go for the level 1 DFD, which we called as the overview. So, here we will just try to give importance to the major process of the corresponding system. So, we have a rule such that this is going to be a balancing rule. The balancing rule, what it says is the number of input output data packets must be equal on the exported level 1 for every process, ensuring the conservation of data across the levels. So, how much ever levels you go on in the DFD, the number of input output packets that was mentioned in context has to be the same. Whatever we have mentioned in the context should have the same numbers in the other levels of DFDs. Okay, so that is what is the idea. So, we will take an example, say manage order. Okay. So, in this manage order is going to be one sub process. So, that sub process is going to be decomposed in the level 1 DFD. Okay. So, here when we consider about the CRUD matrix or CURD, so we have learned this earlier. So, C stands for create, R stands for read, U stands for update and D stands for delete. So, this is going to be the matrix with which we will try to identify what actions a corresponding sub process can have within that corresponding software. Okay. So, when we do this, what we actually come across is that it will prevent the orphan stores and it also validates the data flow and there will not be any inconsistencies. So, just take this as an example. Within this manage order, there could be a create order sub process, update inventory another sub process and confirm shipment. So, these are going to be 3 sub process under a single process called as manage order in level 1 DFD. Okay. So, here this create order may have some impact or some updations or additions it could make. Okay. So, what all is actually identified by your CRUD matrix. Okay. So, assume here we have two different databases. one is your order DB and second is going to be your inventory DB. So, by the name we can understand inventory DB will have all the information about the products and order DB will have all the information about the orders with which a customer has made to a corresponding product. Okay. So, when you have a create order as a sub process, this CRUD matrix will say what all activities are happening. Okay. So, when you want to create order, obviously you have to create a row in the order DB. Okay. So, that is why we have a C in your with respect to your order DB. And updating the inventory, what happens is when you try to create an order, which means that a customer has ordered for a product, it has to be having some influence in the order DB because he or she has ordered that corresponding product. But you have to verify whether that product is available, and if available the quantity matches whatever is required. Okay. So, that also we have to do. So, that is the main reason we are going to read the details from your inventory. So, it is something like you are checking whether the needed quantity is less than the available quantity. So, normally it could be less than or equal to also. Okay. So, say for example, there are say pen as a product and the available quantity is say 10 and the requisition is going to be 5. You want to read and check whether the value is greater than the need. Okay. So, this is going to be the need, this is the availability. So, need should be less than the availability. So, to check that we have to read that corresponding value, and that is why we have the read. So, after you have placed that corresponding order, this has to be changed to 5 because you have already placed an order for 5 quantities with respect to that customer. So, you have to update. So, that is why we have read and update with respect to your inventory DB. Okay. So, next is once the inventory is being done, meaning you have placed the order, the next step could be confirming the shipment. Okay. So, confirming the shipment is not having any influence with respect to your inventory DB. So, you can just have an update statement with respect to your order DB. Why you have only an update? You have already created the row in your order DB, you are just going to update with the shipment information. So, that is why we have this U, which is nothing but your update. So, by having all this information in a CRUD matrix, we are trying to make sure that there is no sub process is behaving like an orphan. What exactly is orphan? It is all alone. So, it is not linked to any of the system or it is not having any valid path. So, that kind of processes will not be available if you are going to use this CRUD matrix. And we can also validate the data flow and check whether it is having consistency or not. So, I repeat what we mean by consistency. So, consistency is going to be a state where everything is going to be true. So, say for example, when you have subtracted the need from the availability, you have updated this 5 in the inventory DB. So, it is going to be true all the time. Okay. So, later point of time when you check for the inventory DB, it should not say 10, it should update as 5. So, that is what is very important. So, this consistency is maintained. So, whenever we draw a data flow diagram, we have some checklist that has to be followed for better clarity. So, one is there should not be any unlabeled flows. So, what exactly it is? Each and every arrow should have a clear singular noun. So, what activity it is going to do. So, that is very important. So, second one is the naming. So, normally it should begin with a verb. Say for example, process order, validate account. So, something like that. Every name should begin with a verb describing the action, what exactly it is trying to do. The third one is there should be consistent entities. So, all the external entities that appear at every level, it should be same across the diagram. Then the store IO balance. So, data stores must have greater than 1 inflow and outflow. So, it means that when you have something in the data flow in the database, there should be an interaction to add on to that corresponding database and retrieve from that corresponding database. So, everything has to be at least greater than 1. So, one single interaction should be there either ways. The next one is data dictionary. So, data dictionary is some information about the data itself. So, it is trying to give you the complex data structures, and it should be defined for each and every entity and the process that is involved in the DFD. The main important validation checklist is it should not have black holes. So, what it means? So, the output must not exceed inputs for any of the process, okay, and no entities should be like a orphan, and it should have some level of interactions such that it is aligned with the software. So, next we will look on to the structured flow chart. So, what exactly is a flow chart? So, we might have learned this flow chart earlier, but how it is going to be used in design in software engineering. So, that is what is dealt here. So, we call this as single entry single exit pattern. So, when you look in a flow chart, it starts with a start symbol and it ends with the stop symbol. In between you will be having many processes like inputs, output, process, decision. Likewise, we have many other processes in between, but when you start at one point during runtime, you will finish at the end. Okay, so there will not be any loops continuously. At one particular point of time you have to finish. So, that is the main important part in a normal algorithm. So, the same thing holds true in this software engineering practices also. So, it is trying to say it is a, we will actually try to explain with respect to a binary search algorithm. So, this algorithm you might have learned in the data structures class. So, this is going to be the algorithm. So, here the main part with respect to software engineering here is that we have a function here, n high is greater than or equal to n low, and there is another condition over here where we are checking for a equality condition. So, these two are going to be the things that we are going to look in with respect to our example. So, this is the very basic binary search algorithm that you might have learned in your data structures class. So, we are only going to concentrate on mapping this decisions, okay, a greater than equal to decision and a double equal to decision with respect to our software engineering, that is it, or with respect to our flow chart. Okay. So, here we have the while loop into consideration. So, the while loop is normally any decision, it is not only while loop. So, in this example we have two decisions, one is your while loop and second is going to be a for loop, and they both are going to be considered as a diamond, which is the structure with which we will do the decision. Okay. So, with respect to the symbols that is being used, we have a start symbol and you will have a stop symbol, and the input will be having this as a symbol. We have decision, process is given as a rectangular boxes, both input and output is going to have the same symbols. Okay. So, these are the main symbols that are being used in your flow chart, and here the while loop which says low less than high feeds the main sequence, and there is a key double equal to array of mid. So, this is going to have two exists. So, normally if loop will have two exists, when if is true what will happen and if is false what will happen. So, it will be having two exists. So, this is also considered as a decision in our flow chart. Okay. And there is, we actually try to map directly from the code to your, from the flow chart to your code. Okay. So, in addition we have this NS diagram alternative. So here it is more or less it is equal to your flow chart, but the main distinction between the NS diagram and your flow chart is that here in NS diagram they will be using segregations. So say for example, here you will try to find a box, okay, and here there are 3 boxes here, okay. So from this what we can understand is that this is going to be one block and this is another block and this is the third block, okay. So some level of understanding could be found when we use this alternative diagram, and the main advantage of using this NS diagram is that the number of boxes is normally equal to the level of complexity. So this is the key features that is listed with respect to the Nazi-Schneemann diagram. So here the stacked rectangles, it represents the sequences of operations. So from the previous slide we can understand there was 3 different boxes, and from that we can understand this is going to be 3 different processes that has to be executed in sequence. And there could also be horizontal splits, so which denotes the loops and branches, and the rectangular topology, it is trying to enforce the structure and it is trying to eliminate the arrow crossings. So since that is one single module, the number of arrows that moves here and there will be reduced. So normally the arrows will be high with respect to one single module and it should not be across the module. So that could be handled using this NS diagram alternative, and this is going to be the main important point. So with respect to your cyclometric complexity, so with respect to this NS diagram, the equal number of conditioned rectangles, so this numbers, it is trying to it is trying to help us calculate the computational complexity. The number of rectangles, it is going to be the number of complexity, the complexity with respect to the cyclometric complexity. So the cyclometric complexity is calculated like this. So V is equal to E minus N plus 2P, where E is going to be the edges, N is going to be the nodes, and P is going to be the connected components, okay. So here our intention when we draw this diagrams is that the complexity has to be less. So when there is a high level of complexity, it is something like when you do some modification in one, it will have its influence and it will have its problem disseminated to many other associated modules, okay. So when you try to make the complexity level, the V level, to less than 10, it will be easily maintainable, okay. So basically cyclometric complexity is trying to tell how efficiently we have written the code, and basically there should not be any crossing lines, and the diamonds should have these number of exits less than 2, greater than 2, and the arrows re-entering the mid sequence. So these are considered as wrong with respect to our cyclometric complexity, and basically when you have this flow charts, when we extract these things, it is good to have depth less than or equal to 3. So more than that is going to have a little negative impact with respect to the implementation. The third topic for the day is decision tables. So first we will look into the example and then we will try to understand how we can draw a decision table. So here assume this as a simple example of similar inventory system. So here we have 3 conditions: first condition, second condition and the third condition. So the first condition is customer type. So what category they are going to be, gold or silver or platinum something, and the order total should be greater than 100. So this is the another condition, and the region being domestic or international, here it is domestic, okay. So these are the 3 conditions that we are going to take for this decision table example. Okay, and we have R1 to R8, which is telling you the requirement. Okay. So, from this what we can understand is that normally when you have 3 conditions and you have 8 requirements, you will 8 rules, we will be having 2 power 3, which is nothing but 8 rules. So, this when you have all the 8 2 power 3, it is trying to demonstrate full completeness and it will not have any contradictory actions. Okay. So, when the conditions are being specified at the left and the yes or no is represented, and based on that we are trying to specify the actions. So, if you consider the customer type being gold is true, which is yes, order total greater than 100 is also yes, and domestic is equal to, region is equal to domestic, which is also yes. So, when all the 3 are going to be yes, you are trying to give a free delivery. Okay. And if the region alone is not domestic, you have given an N, you are trying to give a discount of 10%. So, these are nothing but the actions, and this will be taken on a particular conditions that has been met. Okay. So, this is what is the idea. So, these are going to be the set of rules from which we can come up with the action. Okay. So, from R1 to R8, they are nothing but the rules with respect to this decisions. Okay. So, say for example, with respect to R6, R7 and R8, there is Y with respect to order total greater than 100 and region equal to domestic, but the rest is N. So, which will say it has a standard delivery. Okay. So, these are nothing but some examples with respect to how we can create a decision table. So, decision table is fine. What exactly is limited entry? So, limited entry here specifies, so these are nothing but the entries. Okay. Within the table, these are nothing but the entries. So, this entries should be in a fashion that it is answering some yes or no questions or something in numbers. So, if you are trying to give something in text in a very big format, that will make itself a complicated one. So, that should be avoided. So, that is what we call it as limited entry decision table. So, after understanding how to build a decision table, we will exactly find the process. Okay. So, this is trying to say a step by step process to ensure completeness and consistency. So, the first step here is that identify the conditions. So, we have to list in all the independent binary conditions. So, why binary? We are trying to get the answer as either yes or no, either 1 or 0, something like that. So, this is trying to give you a simple example. So, that is why it is binary, but it is not always binary. You can also go for non-binary conditions also. The second is enumerating the rules. So, whenever you have n conditions, there could be 2 power n columns which are represented as rules or the requirement with respect to this decision, making this decision. So, we will be creating 2 power n columns with respect to all the combinations. Once all the rules are being enumerated, we will go for listing the actions. So, we have seen the example in the previous slide where you will be having 2 power 3, which is nothing but 8 set of rules. So, 8 different patterns. Okay. So, from that pattern we have to identify what actions can be taken. Okay. And the last step is that we will be trying to, here we have given as X for triggering an action, and that could be taken for triggering a corresponding action. So, I will go back to the previous example so that we can be clear again. So, as I said, the first is setting the condition. So, this is the first step. Second step is, since here n is equal to 3, the number of conditions equal to 3, the number of rules is going to be 2 power 3, which is nothing but 8. So, we have R1 to R8. Okay. Third one is you will be entering this table. So, it is something like your binary. So, it starts from 0 0 0 to 1 1 1. Okay. So, this is 0 0 0 0 0 1. So, it goes from binary 0 to 1, 1 to 8. Okay. So, based on this you will go with the actions. So, this X is being marked for whichever set of rules you are trying to have. Okay. So, this is the idea of creating a decision table. So, this is the exact phase. So, the sequence rules by business priority will be taken to simplify the inspection and testing. So, how we can optimize and verify the decision table. So, this is another important aspect. So, one is optimizing. So, what exactly is optimizing? We have to reduce something with respect to the loss, or we have to increase something with respect to the profit. That is all. So, we are trying to reduce the redundancy. So, we have understood that the entire decision tree is based on the number of conditions that we follow. If we increase the number of conditions, the decision table is going to be like exploding in exponential, right. So, we have to make sure the number of conditions has to be less and it should also be meaningful. Okay. So, whenever there is adjacent rules differing with irrelevant condition, then only then you can merge one or two conditions. And sometimes you can also use don't care dashes to shrink the table size. And by maintaining all these diagrams, decision table, we are trying to ensure that there is a 100% condition coverage, and that is done using our decision tree. Okay. So, how to validate? So, when there is say two rules, the same condition should not trigger different actions. Okay. So, no two rules with same conditions. This is very, very important. So, no two rules with same condition should trigger conflicting actions. Say for example, agree or disagree should not be done with the same condition. Okay. And we have to make sure there should be minimal set of rules. So, this is what I have tried to say. So, everything is based on the n, which is nothing but the number of conditions. So, that has to be minimal. And the version control. So, you can have multiple such decision tables is often updated throughout the software engineering process. So, that could be validated and pushed to some centralized repository. Here we have mentioned that as Git. So, the last one is HLD versus LLD traceability, high level design versus the low level design traceability. So, basically with respect to high level scope, we are trying to say what we are focusing on. So, it is trying to define the system architecture and the major components. So, something like we are creating a context DFT. So, context DFT is a level 0 DFT. It is a very abstract way with which we are trying to say what all inputs come to the process and what all outputs are expected from the process. So, that is what is the importance. So, how it is going to interact with the external world. So, our goal should be like for the next DFT, the level 1 DFT should be less than 7. Second, we went with your decision tables. So, this is trying to basically find what could be the rules and everything, and it is trying to cover the major revenue impacting business rules. Okay, and it should be like 80% coverage of all these business rules. Non-functional requirements. So, in your DFD or in any other diagrammatic tools will be mainly concentrating on the functional requirements, and here we adding the scope for non-functional requirements like your security, scalability, performance and everything. So, this will not be listed by the stakeholders, but this is very much important in making the 100% stakeholder sign off. So, low level description, the low level design, what it says is it is trying to refine whatever is mentioned in the high level. Okay. So, there we are answering what, and in LLD we will try to focus on how exactly it is trying to do. So, wherein we come with your flow charts, pseudocodes, decision table and the data specifications. Okay. So, this is what we have learned. So, what is pseudocode? So, pseudocode is much similar to your flow charts, where we do not have any diagrammatic picture, but we will try to say in natural language how we are going to execute that corresponding process. So, it has some set of notations with which it is trying to give a idea of changing the requirements to implementation. And decision table we have already said, and the data specification, it is trying to deal with the data or the databases. So, we have to specify the length of the field. Say for example, in case of order, we will be having the product name, say quantity. So, each and every field will be having a specific length. So, that and all will be mentioned, and how many columns has to be, everything has to be mentioned. So, this level is called as your low level. So, we are speaking with respect to the size of the field inside your database. So, likewise we have the refinements. So, basically the output and traceability is our next topic. So, the final output of the pseudocode that can be directly transcribed into unit testable functions. Okay. So, normally flowchart and the pseudocode, they are used to convert that to a particular code. Okay, be it any programming language. This pseudocode, by the name we can understand, it is a false code. Okay, so much prior to your code, we are trying to convert each and every part that is written in the pseudocode to a particular programming language, say it Python, Java or C or whatever. Okay, and each LLD element will have a trace tag. Okay. So, trace tag itself we can understand it is going to be linked with something. So, what exactly it is going to link with? With the parent HLD. Okay. For automated impact analysis. So, HLD is high level design, and HLD will be connected with many LLDs, and this LLDs will have a trace tag with which we can identify to which HLD it is linked on. That is all. So, this is another example. So, from which we can actually do the traceability. So, traceability as a word, what we can understand, you are doing or working with some module, we are trying to go back and find where it is attached to or from where the issues began. Okay. So, that is what is the traceability matrix. So, here we can understand the table, it shows HLD ID, LLD ID, there is a test case ID and the status. Okay. So, these are nothing but the small functionalities. So, this functionality has a corresponding test case, say test case 1, and that has been passed. Okay. So, once the test case has been passed, it means that this functionality is completed. Okay. So, once it is completed, we have to link this code to the corresponding HLD. Okay. So, with which we can have the entire traceability of where it has come from and where we have to give it back. Okay. So, normally this continuous integration scripts, it will be evaluated daily after working hours, and we have to make sure that the traceability is having a coverage of more than 95%. So, if suppose your percentage is going to be less, it is something like you have an orphan process that is not linked to any other HLD, which is actually a waste of that time, right. So, when your percentage is higher, it means that we have the traceability in the process and we have the knowledge of to which high level design it is going to be added on. Okay. So, this is going to ensure the LLD element is tested for every change and that is traceable, and the status could also be changed as and when it is going to be executed. So, here we have an example of pass and pending, from which we can understand the second LLD, which is linked to HLD DC002 is still pending. So, this test case is not yet executed. So, as a summary, in this lecture we have understood what is a DFD and what are the process in drawing the DFD with some examples, and then we moved on to the structured charts, flow charts. So, flow chart, how it is going to be beneficial to change from the requirements to design, and we have also seen about the pseudo code also, and then we went on to decision table. So, here creating a decision table is itself a difficult job, and once we have a very good decision table, we can create very good business rules and find 100% coverage in the business rules. And then we ended the lecture by understanding the traceability between the high level design and the low level design. Thank you.